In this video, I will implement Inception-v4 pre-trained model with PyTorch on a drone dataset. So the original dataset is available here from this website, but it's also available in a pretty popular Kaggle dataset, where the name of the dataset is Aerial Semantic Segmentation Drone Dataset. Hello, my name is Rohan-Paul, and very welcome to my computer vision and deep learning YouTube channel. Let's get started. And I already have downloaded the dataset in my local machine. So let's quickly go over the overall structure of the dataset and also the problem that this dataset presents to us. So here in this section, they mention the dataset overview. So the semantic drone dataset focuses on semantic understanding of urban scenes for increasing the safety of autonomous drone flight and landing procedures. The imagery depicts more than 20 houses from nadir, that is a bird's eye view, occurred at an altitude of 5 to 30 meters above ground. A high-resolution camera was used to acquire images at size of 6000 by 4000 pixels. So these images are really will consume a lot of data. So these are 6000 by 4000 pixels images. The training set contains 400 publicly available images, and the test set is made up of 200 private images. Yeah. So, and about the tree structure of the dataset, if you go inside this dataset, you will see the subfolder semantic drone dataset, and also inside it I will have original images and label images semantic. So if I click on the label images, actually first click on the original images, then it will make sense. So this is my original image. All these are taken from drone. So this is just one example. If I go into another image, here is another example, and the label images are the masked image, so they are properly classified. So these are the mask of the original images, and this is another example. All right, so yep. So with that, that's kind of the overall data, the tree structure of the input data set. Now let's go to our VS Code. Yep. I'm just importing the regular imports, mainly NumPy, Pandas, Torch, Torch Vision, Argumentation. Then I have to define a path, because I am using both Kaggle kernel and also I'm doing it in my local machine. So I have two paths defined. Path in local machine is what I'll be working right now. All right. So I'm just initially going to do a very basic EDA to just check out overall how the data looks, how the images looks. My image list will be equal to list here is actually it will be root ing path. So now I'll be creating two lists for the images and also the mask. Oops, let's just came outside. Plus I for I in image list. Similarly, I got to do for mask list. Root mask path. And finally, image list will be get sorted. Sorted mask list. Now I want to print the number of images. Images are len image list. And also I want to print just to image, actual image. So that would be image list 0. Similarly, print mask list 0. And if I run this cell, yep, I got number of images 400 as expected, and this is just 2 example images. All right, now I want to plot a couple of images, and so let's do a plotting code. Go to 10. You can choose, of course, any index here. I'm just choosing an index number here. Image equal to image io dot imread image list. Choose n. Actually, if I name it like this, it will be better. And then print. Very important to check the shapes. Mask equal to image io read mask list in mask list index. Print shape. And now let's plot. One row, 2 columns, and fig size will be, let's give it 12 by 10. Array 1 dot ImShow. It would be mask. Alright, let's set title mask image. Let's run this cell. Yep, so that's my image in the data set. This is an example original image, and this is the mask or the label of this image. All right, now for I want to do extract my root file names and actually define my root file root directory, and also extract all the file names to construct a data frame. So this is a little data preparation part. So number of classes, we know that There are 23 of them in classes equal to 23. And now I have to import a few other things from OS. Import list. Oh, I think this I have already imported earlier. So from os.path, import is file and join. Now I have to define a method. Let's keep all my actual methods in a utils file, because there will be a lot of small utility methods. So let's define a util py, and also let's define a train.py. Okay. So in my utils.file, I will define a method for creating a return df containing the image IDs. Get image ID df So I'm extracting all the file names. So I'll be using this syntax: f for f in list dir. Within that, I'll pass root and root img path, and root img path will come from argument root img path. Oh yeah, I did not import because it's a separate file. I need to import few things. So let's import my entire pack of things, which will be, later I can clean it up. Yep. I definitely don't need argumentation over here, but let's keep it for now. All right, listdir. Oh, I still did not import my listdir thing. Yep. So let's import that. Import argumentation. Yes, now that makes sense. This file. Oh no, I'm still short of listdir. Why is that so? So I don't know. From OS, import listdir. Yep. Root image path. For f in listdir root image path. If I need to check for if the file is really a file. If is file, within that I'll pass join root image path and f. Yes. Now for file name, in file names, name.append append file name dot, I just want to append only the name, excluding the extension, file extension. So I need to split it by a delimiter, and my delimiter in this case will be a dot, and then from this I need to take 0 index. All right, now return pd dot data frame. I will have one column named ID that will have the name, And I will also okay, that's my this thing, and then index will be equal to np.ar a range 0 to len of name. Okay, now if I go back here and do, oh, I need to import all these new files that I just created. So from utils import star, similarly from prime import star, run this cell again, and now I will do this df equal to get image id df. To that I will pass my root directory, root image path, oops, sorry, root image path, and I'm just going to print the len of df. Let's run this cell. Yep, so I got this 400, and I also want to print the head of this df, df.head to, and that's how my data frame will look like. Only the ID column and with all the image IDs taken from the image files. And then I need to split the data set into train and test. The values. So, all right, and test size will be 10%, and random state, let's keep it equal to 19. Now I need to split these xtrain further into train and validation. Train and x val equal to train test split df. No, this will be now, this will be my x train and val. Yep, this one. And test size, I will keep it 15%, 0.15. Random state 19. Let's print to check that they are all fine. Print size will be len xtrain test size xval, and sorry, this will be test actually, yeah, and last one will be validation size. All right, 360, 306, 40, and 54. And now I am going to do Dataset Generator. So I need to define a class. Actually, let's do that in a separate file. DataGen. Okay. Yep. I am going to, again, I need all those, just copy everything, and whatever I do not need, later I'll clean it up. Class Gen, it will take dataset. The first function is the initializer underscore underscore init to itself ing path mask path. Then I need to pass the x mean std transform equal to default value should be none, and patch is patch is equal to false. So this patch is something we will define later, because here the original training image said really of high dimension, that is 4000 by 6000. So it's better when you have such a high dimensional training set images, it's better to train it with patches. So I'm keeping an option here that if my patch is true, then I will have a separate mechanism going on later that I will define later, that the training images will be divided into patches of images, and the training process will be executed on those patch. So but that will be controlled with this argument. So self dot ing path equal to ing path, then self dot mask path, self dot x, self dot mean, self dot std, self dot transform, self dot patches. All right, now my next method is len self return len self dot x, that will be capital X. And now I need to define the all important GetItem method, which will actually get me the item, that is the image from the training set given the index. So get item self, and it will take index of the item as an argument. First I have to read the image, so cv2 dot imread self dot img path, and then self dot x pass the index, and also the file extension. I need to mention all my training images are in jpg, so jpg. Then convert color cv2 dot cvt color image, and I need to convert from bgr to rgb, so cv2 dot color dot actually bgr to rgb. Yes, mask will be cv2 dot imread self dot mask path and self dot x idx, and a file type for all my mask were png. So, and also cv2 dot imread grayscale. And now applying the transform based on a boolean. If self dot transform is not none, I don't need the second, none, then my augmentation will be self dot transform image equal to img mask equal to mask. All right, when image equal to image dot from array, from array, sorry, actually from the augmented image I need to get the image image. Yes, and mask will be equal to all mask. Actually, this also will be small a. Yeah, so yep, that's it. Now I need to do t equal to get apply few transform t dot t represent my transforms. So let me check. Have I? Yes, torch vision dot import transforms as t dot compose, and then my compositions will be t dot. The first one is always to tensor, and to that next one is t dot normalize, and for normalizing I will do self dot mean and self dot std mean and self dot std standard deviation. Okay, then image now will be p and g after the transforms, and mask will be torch dot from numpy mask. Yes, and I also convert to long. And now finally I need to take care of these patch argument here, patch boolean argument. So if self dot patch self dot patches, 1 second. Self dot patch, I think I wanted to name it self dot patches because that makes more sense. CHES. Right, so that means it will be self dot patches. In that case, I need to invoke another method that I have not defined yet, but let's just do it here. In that case, self dot get. The new method that I'm going to write in a moment will be named as get image patches, and that will return me image and mask. So this method will take the image and the mask and will return me image patches and mask patches. So let's write that method now. Div get image patches self image mask. Yep, makes sense. And also another thing to point out that I referred PyTorch discussion forum for writing this method. So that's the discussion forum that I referred to here, and they have given there's quite a bit of important discussions around how to make patch making, how patch making is executed in PyTorch. And the fundamental problem is same, that when your images are of larger sizes, for example in this case, the original question asked that I have 3-dimensional data samples ranging in the 500 by 500 by 500. Such huge pieces of data of course can't be fed to the network in one piece, and therefore patching is required. So I want to create a 64 by 64 by 64 patches. So in my case, the data are 4000 by 6000, and I want to create patches of, let's say, 512 by 768. So what this will do, a little documentation here. Split images into patches of size 512 by 768, height and width respectively. So let's define my kernel size first. KH and KW will be 512, 768, That's my kernel size. Also, I have to define the strides, and because I do not want to have any overlapping area, so my strides will be same size. DH and DW will be 512 by 768, and that's my strides. STRIDES. Now, image patches. Here, one thing that I am going to use PyTorch's unfold method. So let's quickly go to their documentation first. And here I'm looking at the unfold method documentation in PyTorch, and basically it extracts a sliding local blocks from a batched input tensor. And I definitely suggest you read through the documentation. And in terms of the arguments it takes, the first one is kernel size, then dilation, then padding. Now there is also a very beautiful Stack Overflow post on these that where the question is, how does PyTorch's fold and unfold work? And there's some great answers here. So basically I was just reading through this answer. So the unfold and fold are used to facilitate sliding window operations like convolutions. And that's what I'm going to do in my patches, where I have to slide a kernel to get my individual patches from the original image. So yeah, let me see if I find anything. Anyway, so this visualization is kind of helpful. So if you have an original tensor like this, what unfold will do, it will make few folds so that the resultant tensor will give you something like these smaller squares. So let me start coding it here. So my image patches will be dot unfold. To that I pass 1, then KH DH. That is my kernel size, kernel height, and the height of the stride. And to that I have to unfold again. And this time I gave it my kernel KW and also DW. That is for the width. All right, and now my image patches, I need to make more operation on these. Patches equal to, now I'm going to use the contiguous method, and also for reshaping I need a view method. All right, so ing patches dot contig contiguous, and this will create a copy of the tensor where the individual elements are placed in a contiguous fashion. And view, the first one is 3. The next dimension I want it to be inferred, so -1, KH and KW. I need to even do a permutation on this to rearrange my dimension. So image patches dot permute, and so what I want to do is place the get image patches number in the 0 index. So 1 0 2 3. And now for the mask, and do the same for mask patches. Maybe at least CTS equal to mask dot unfold, then 0 KH DH, also another unfold for the width, and it will be, this will be 1 KW DW. I need to make the array contiguous as well here. So mask patches equal to mask patches dot contiguous, and then view will be -1 kh kw. That's it. Now I can just return the image patches and mask patches. All right, and now I am ready to bring forward the models that I want to apply in this project. So we have already imported the segmentation models PyTorch as SMP. So my model actually will be, so let's go to my notebook, right? Dataset Generator. We have already taken this to another file, so I can delete this one. Let's bring in my model here. Model equal to smp.unet, and I'm going to use Inception-v4. Now we can actually go and quickly check PyTorch segmentation models, and this is their official GitHub repository. Now under the models, they will have all the models that they support, and here we can see one model to 3 models actually under Inception. So I am going to use here Inception-v4 here, which has 41 million total parameters. Of course, I could use some of the models from here. For example, I could use VGG. There are so many VGG supported under this package. I could use MobileNet. Also, there are quite a few MobileNet models supported. Anyway, so I'm going to go with Inception-v4. Encoder weights ImageNet, and we have total classes of 23, so I am going to give classes equal to 23. Activation none, and let's give encoder depth of equal to 5. And the last parameter I have to mention here is decoder underscore CHNMEL, decoder channels that would take 256, 128, 64, 32, and 16. And if you are interested, you can go through the documentation to know about what all these arguments actually signify. Let's just go to their documentation. So for example, encoder depth, I used 5, and the documentation talks about encoder depth here, which is a number of stages used in encoder in range 3 to 5. Each stage generates features 2 times smaller in spatial dimension than previous one. For example, for depth 0, we will have features with shape NCHW. For depth 1, NCHW, NCHW by 2, W by 2, and so on. Default is 5. And then the next argument I used decoder channels. So this is decoder channels over here. So this is a list of integers which specify in channels parameter for convolution used in decoder. Length of the list should be the same as encoder depth, and I do have the length of this list as 5, which is my encoder depth. It also takes some few other things as their argument. Encoder name, this is the first argument, which is the model actually I'm using. It could be all those separate models like efficient net, mobile net, and so on. And decoder attention type, decoder use batch norm. Okay, this is whatever is a default. Let's be with that. And activation function to apply after the final convolution layer. Available options are sigmoid, softmax, log, softmax, stan, h, and identified. All right, so let's go with whatever I have for now. Okay, so that's my model. And now if I just type model here, that will print my model. And of course, because it's a large model, it cannot print the entire structure right here inside my Jupyter notebook in VS Code. But anyway, so that's my model. Now I again have to code up few utility methods. For example, I need one very important metric in object segmentation called pixel accuracy. And I have a separate video on this topic, so you can check my channel to go over that video. But here I am going to quickly code it up. Pixel accuracy, that will take predicted image and the mask. This is just in simple words, pixel accuracy in image segmentation is equal to correctly predicted pixels divided by total number of pixels. Let me put that in a comment. Pixel accuracy equal to. All right, so now because in these pixel accuracy I'm only dealing with scalar values, so I do not need to carry the unnecessary gradients with PyTorch tensor. So I am going to define a context manager here with torch.noGrad, and then predicted image equal to torch.argmax. And I have imported, I think, torch.nn.functional as f. So I need to bring in softmax here, f.sofp softmax predicted image over dimension equal to 01. And am I doing it right? Dimension equal to 1, yes. And also I have to give a dimension to the argmax. Yes. And correct will be where two tensors equals, and my two tensors are predicted image and mask. So I am going to use torch.eq, and then to that I'll pass predicted image and mask, and put an int over here. And then my accuracy will simply be the division of these above two variables, but I want to make them a float value. So correct.sum, similarly float correct.numel. And so this numel, this returns me the total number of elements in a tensor, and that's because here I have to use here numel because these two tensors that I am considering here both are a three-dimensional tensor here, three-dimensional matrix, that is batch, height, width. And so I cannot just use len of the tensor. To get the total number of elements of that tensor, I need to get numel, this particular method of PyTorch. All right, with that, I have the correct and I have the accuracy, so I can just return accuracy. Yeah. I also need to define another very important metric called mean intersection over union, or mean IOU. Now, I have a separate video just on this subject, so you can just go over that video. I'll put the link of that video in the description. So basically, this is the definition of IOU, which is intersection over union, and that is 100 into true positive. That is, it's a ratio of true positive divided by true positive plus false negative plus false positive, and where the true positives are those pixels that belong to the class and are correctly predicted as that class. False negatives are those pixels that belong to that class but are incorrectly predicted as a different class. And lastly, these false positives are those pixels that belong to a different class but are predicted as the class. So after you calculate your intersection over union, the mean IOU over the entire data set should be calculated as follows. That is, this is kind of the pseudocode of calculating mean IOU, which is, for each class, calculate the total area of intersection and area of union over the entire data set. Then for each class, IOU equal to total area of intersection divided by total area of union. And lastly, the mean of IOU for each class is your MIOU. Now, I already have defined this function while doing the previous video on this subject. So I'm just going to copy that code and paste it in my utils files over here. All right, so that's my code for mean IOU. And for explanation of these, again, you can just go over that video, because I have coded these, I have explained these in much more detail in that separate video, so I do not want to repeat it here again. All right, so that's my, I think all the utility methods, kind of the most important utility methods, are kind of defined. So I need to do my training methods right now. First, let's just copy all the imports. All the imports. Yeah. Now here is all important training method. First, I'm going to define a method to get the learning rate, which is it will take optimizer as an argument, and for param group, in optimizer.param groups, I need to do return param group, then take the key of LR. Okay, and now my training method. This will be slightly longer. It will take number of epochs, epochs, model, train, loader, val loader, criterion, and optimizer. I still need more, which is my scheduler, and also I need the same thing that we discussed. We need to control for patch. So that is whether I would be dividing the images patch by patch, or whether it should be kept at false. So this will be a Boolean argument, and I am defining the default value to be false. Why this is coming? What's the problem? Yeah, epochs, there's a dot after that. All right. Am I doing everything correct? I think so. empty cache, defining a list to hold my losses of the train set. Losses train would be similarly losses test, and then val IOU also will be, and also val ACC accuracy. Okay, train IOU and test, sorry, train accuracy equal to an empty list. And what else do I need? I need learning rates, LRS equal to empty list, mean loss equal to, make it infinity so that I can, it is just for comparison, np.infi. So it's just a starting value with which I'll be comparing during my training. And decreases, DECRES, yes, put it to 1. And also I need to define a hyperparameter sort of thing, that is number of times the loss is not improving while I am doing the epochs training. So only when after this many number of times the loss is not improving, then I am going to stop the training further. So define it, 1 second. Number of times loss not on the ROVING, starting value of it will be 0, and it will be a counter, and it will be this number will be increased, and then when it touches a particular value, a particular number, for example 6 or 7, then for that many continuous times loss was not improving. That means I need to stop the training further. And then transform my model to device. I have not defined device. Okay, let's define device. Torch.device, CUDA, if torch.CUDA dot is available, else CPU. All right, and now coming back to my model, where, yep. So that's my model, the 2 device, and then I am going to define a time frame. So let's consider it fit time, which will be time. And now start the loop of the epoch. For epoch in range epochs, first the time, dot time is time, dot time. I need to keep track of my running losses. Running loss equal to, so the starting value of these will be 0. Similarly, starting value of IOUs 4 will be 0, and accuracy will be 0 as well. And now my training loop. Model the train. And remember, this model is a pre-trained model of Inception-v4. based on ImageNet dataset, that is ImageNet weights. So I have to use the second inner loop here for I data, because it will return me I'll be enumerating over the train data loader, which we have defined earlier. And train data loader actually in this function is coming from the arguments. We already have used the data gen class to get my train loader. So I will do this, will give me the index and the data in enumerate. I have to make use of TQDM so I can see the progress clearly, and inside that I will be passing train loader. Then my training phase, let's define the data contains both image tiles, that is image data, and the mask tiles. So let's define accordingly. Tiles, mask tiles equal to data. And again, here I need to make the code. I need to write some code if the patch is true, that is, if I'm training the images by dividing it patch by patch, then there will be one set of code, otherwise there will be another set of code. So if patch, am I doing it right? PATCH, then if patch, then I will be making use of image tile.size to get my batch size, number of tiles, channels, height, and width. So image tiles dot size will give me batch size, then number of tiles, then channel, then height, and the width. Yeah, I was just yeah, I think this is right. Sorry for the delay here, because I was just lost in some other logic thinking about that. Yeah, let's move. And similarly, I need to do image tiles. So from these image tiles, I need to reshape it. Let's do image tiles equal to image tiles, dot view -1 channel height width. Yeah, so I'm taking the channel height width and keeping the first dimension as inferred. Similarly, I have to do the same for mask tiles equal to mask tiles dot view channel height and width. Okay, so that's when it is when the patch is true. So now come out of that, and my image now equal to image tiles dot to device, and similarly mask will be mask tiles.toDevice. And now I need to do the forward propagation. So because I have all the elements now to get the predicted image, so all I have to do is pass the training image to the model, which will give me predicted image equal to model, and to that I pass image. So my loss will be criterion. Have I defined criterion here, or is it coming from, have I defined it in the, yes, I have defined it in my arguments. So I need to later, when I execute this method, I need to define a criterion. For now, loss equal to criterion. To that I will give predicted image and mask. Ideally, in the ideal world, these two should be exactly same, but here the difference between them will be my loss, which I am supposed to reduce through this training. So now evaluate my metrics. Metric to do evaluation. It will be metric. And here where I'll be using my previously two methods that we have defined in here, that is pixel accuracy and mean IOU. So I need to import these utils file in my train.py from utils import star. Also just import from data, why did I name it data get? It will be data gen actually. Data gen. All right, and I think I have made the mistake here in this notebook as well. Utils train, yep, from the data gen import, it will be gen, yes. So in the train as well, data gen import star. And now I will have the access to my MIOU and pixel accuracy methods. Metric for evaluation. So here let's define IOU. IOU score will be equal to plus equal to plus equal to what do I have? Mean IOU. To that I need to pass predicted image and mask. And pixel accuracy, let's just do accuracy here. I do not want to mix up some naming here. That will also be plus equal to pixel accuracy, predicted image, and mask, yes. Okay, so that's my evaluation, and now I need to do backward propagation. For that, loss.backward and also optimizer dot step to do the weights updation. And now let's clean up the slate by with zero grad. Optimizer dot zero grad. I'm just resetting the gradients over there. And now my learning rates, these this array that need to be updated. So lrs dot append, I need to do get lr. To that I pass optimizer, so that will get my learning rate and append that to the lrs list. And also I need to do scheduler dot step, update my running loss, which will be plus equal to loss dot item. Item will extract the scalar values from the tensor. Okay, that's where these for loop ends for I data in enumerate. So now after ending this loop, now because inside this for loop I have a if loop as well, so by the Python's convention I can use a else clause here. So here I'll be, this is very specific to Python. Probably you already know that in almost all of the languages, to use a else statement you need a if statement before that. But in Python, when I have a for in loop and also some if conditional statement inside the for in loop, I can use an else statement after that for in loop. So else model dot eval. Now I'm in the evaluation mode, and so I need to define some variables. Test loss, starting value 0, test accuracy, starting value 0, test val IOU score, starting value 0. Okay, now I need to do, because this is my validation evaluation stage, so I do not need to carry the gradients with the PyTorch's tensors. So I'm going to do a context manager of with torch.no grad. Then for now I need to loop through my validation data loader. So for I data in enumerate tqdm val loader, which will give me image tiles, just like in my training loop, image tiles, and also mask tiles equal to data. Okay, data. Now what? Now I also yeah, so let's do the patching control over here, just like in our training loop. If patch, then I need to get my so just I'm copying from here to be faster, because it will be the exact same code. If patch, then oops, yep, so that means if patch, batch size, number of tiles, channel height, width gives are obtained from image tiles.size, and then image tiles becomes reshaped, and also mask tiles becomes reshaped. Only difference is in mask tiles, let's delete this channel, and yeah, looks good. So now also image equal to, actually again I can copy from here because it's exact same code. Loss, predicted image, mask, yeah, predicted image, test accuracy, yeah, up to this I should be able to just copy. So image styles to device and sorry and mask styles, a mask or the mask style to device. Okay, and then I do forward propagation, which is, oh no, I don't sorry, I'm in my evaluation mode. So after I transfer both of image and mask to device, then I need to calculate, one second, I need to calculate my predicted image, model image. Yes, looking good. Evaluation. Actually, let's rearrange it a little bit. Metric to evaluation. So first I'm transferring image and mask to device. Then I'm getting the predicted image by invoking the model and passing image to that. And then some of these evaluation metrics, and to differentiate with the training, let's name them val IOU score and test accuracy, and that would be mean IOU here and pixel accuracy here. Okay, now my loss function, which is criterion, predicted image and mask, and also test, update the test loss by doing plus equal to loss.item. Yeah, that is kind of looks good. Okay, now come out of these loop, inner loop, and calculate the IOU, mean IOU for each batch. That will be mean IOU for each batch calculation. So losses train dot append, and what I'm going to append is running loss divided by len of the train loader. That will be my mean IOU for this batch. Similarly, I need to losses test dot append. I need to append test loss divided by len of val loader. Losses test dot append. Yep. Okay, that is done. And now check if the loss is decreasing, and if it is not decreasing, I need to stop the training. Checking for loss decreases. So first I need to compare my mean loss. Remember, we defined mean loss. I think where did that go? Mean loss was defined here with np.infinity. So if mean loss is greater than test loss divided by len val loader, then print loss decreasing, DCR, yes, I mean loss decreasing. Let's do a little formatting here. So that would be dot 3f and also dot 3f, and then I'm going to do my formatting. Sorry, here I have to do format, then because loss is decreasing here, so I have to show both the mean loss and the decreased loss. Mean loss, comma, test loss by len val loader. Now update the mean loss. Okay. Well, loader, because this is the average loss. Decreases. Update the counter of decreases because it actually decreased. If decreases modulo 5, only then I am going to save the model. Print saving model as loss is decreasing, CRU decreasing. Torch.save model, and because this is Inception-v4, Inception-v4 MIOU. Now a little formatting. /.3f and .pt. Format val IOU score divided by len val loader. Okay, now let's come out of these decreasing loop, and also I need to cover when the loss is not decreasing. Not decreasing, then if test loss divided by len val loader is greater than mean loss. Remember, mean loss was initialized with np.infinity, and it gets updated with each epoch. So as soon as this latest loss is more than the mean loss, that means loss is not decreasing at this step. So I need to do the corresponding actions for that. First get the mean loss equal to test loss divided by len val loader, and then I need to print if loss not decreasing for, actually I don't need this formatting here, I just need the variable num. What was the variable? Num of times num of times loss not improving. Time. All right, and if so, my strategy is that if number of times loss not decreasing equal to 6, then I'm going to break from this loop. That means I'm going to stop the training at that stage. So num loss decreasing equal to 6, then print loss not see that yes, decreasing for 6 times, hence stopping training ing and then break. All right, now I need to update the IOU and the accuracy list. That is, we defined these variables, that is val IOU, val accuracy, train IOU, train accuracy. And here I am going to update those lists. So I am out of the if loop. So updating IOU and accuracy. Train IOU dot append score dot len of, remember again, this is the average, so I need to divide by train loader, number of samples in this train loader, and do the same for train accuracy dot append and accuracy by divided by len train loader val accuracy dot append accuracy. This will be val accuracy, this will be test accuracy, test accuracy, and before that I need to update also the val IOU and it will be val's IOU score. All right, up it will be val loader. Okay, now print few things here. So what I'm going to print is various statistics during the training. So print epoch there's quite a bit of formatting that need to be done here. So here my epoch will be printed. So dot format epoch epoch plus 1 because it's 0 index and OCHS. So this is current epoch and this is the total epoch. All right, now here it's a little comma, and the next thing is train loss. That would be slice dot 3 f. Okay, sorry, style of 3f, and I am going to print here the train loss. So dot format I'm going to do running loss divided by train divided by len train loader. Few more printing for logging during the training. All right, and now I need to define a history dict variable. Train loss is my losses train, then val losses test train IOU would be my train underscore IOU, and val IOU will be val underscore IOU, and also train accuracy is train ACC, and the okay, I have val ACC as well, and lastly I have learning rates, which are the list containing the learning rates. Okay, finally return from my train. Okay, before that I just want to quickly print the total time. That would be slash 0.2f in minutes, and dot format time. And from that I deduct the fit time, divide this by 60, and that should give me the total time taken, and return from this whole train method this final history object. All right, that's where my train method kind of ends. It was a very long method indeed. And now I am back at my notebook, because here is where I need to execute these train file, that is a train method. So now I am ready to execute my training. All the epochs will start running now. So let's define max LR to be 1e minus 3. Sorry. And epoch, let's keep it at 15. Weight decay, IGHT, DECAY, keep it at 0. Actually 1e minus 4. And my criterion will be equal to cross entropy loss, CROSS, entropy loss. Optimizer, I'm going to use Adam W. So optimizer nn.optim.Adam W. To that I pass model.parameters, METERS, and then my LR is max LR, weight decay, and scheduler, SCHEDULER. That would be my torch dot sorry, spelling mistake, dot optim dot LR scheduler dot, I'm going to use one cycle LR, and to that I pass optimizer and also max LR, and epochs will be epochs, and steps per epoch will be the length of the train data loader. So steps per epoch equal to len train data. Okay, my name was train data LODER. That's it. Why is it saying it's not defined? Train loader is not defined. Let's find out why. Yeah, I think I have not defined the train loader. That's because I did not execute. I have defined all the data generator methods here, but I don't think I have executed that. So yeah, we'll do that in a minute. For now, let's just do that first. Otherwise, these undefined variables error will keep popping up. So here is where I am going to execute data loader. That is execute all data loader methods. And okay, first I'm going to define a list of mean and standard deviation. So that would be this, and then my I need to bring in all the augmentation method from the augmentation library. So I have already imported augmentation as A here, so it should be easy now to do all the augmentation here. So T train equal to A dot compose, and here is where I am going to define all the augmentation. A dot first one is resize. So what does it do? It composes, and one second, let me resize. Okay, anyway, just resize will take my size parameter, so I'm going to give it 704 and 1056. So it resizes the input to the given height and width, and the first argument is height and the second argument is width. That is used to specify the interpolation algorithm should be one of CV2.inter nearest interlinear. All right, so I need to specify an interpolation, which I will select inter nearest, INTER inter, why it is not coming, inter EOLATION equal to CV2 dot it will be caps INTER inter nearest. Oops, my enter does not take NEAREST. Yep. And my next one will be A dot horizontal flip. Horizontal flip, and then also I'm going to do a grid distortion. Sorry, grid distortion. A dot grid distortion. Yep. So this will be num steps, count of grid cells on each side, distort limit. So and it will take a p-value as well, which is a probability, right? Yep. So just grid distortion, and this will take a p-value of, I'll give it 0.2. All right, now I think I need to do replicate the same for my T validation set as well. So T val A dot compose, then A dot resize, interpolation nearest, a horizontal flip, and then grid distortion. Okay, now bring data GENERATOR generator, and this will be my train set equal to data. What was the name of my why it would be gen, data gen, I think. All right, now Let me quickly see. Data gen, right. So my train set is data gen, and then first it will take the path. So my path is root image path. Then for the mask, root mask path, and xtrain, which has been defined at the top, that is xtrain and xval after applying the train test plate. Xtrain, also it will take mean std, then PreTrained for all the transformation, and patch, keeping it false. Similarly, I have to do for my validation set, val set. All these things will remain just the same. Root image path, root mask path. Only here the changes. Xval, then here pval, patch equal to false. Now keep the batch size equal to 3, because these are very large images, so I'm keeping the batch size rather at a very low number. Now finally my train loader equal to will be data loader root image path, root mask path. That is what it suggested, but in my case that will not be so. In my case it will be train set batch size equal to batch size, and keeping shuffle equal to true. Similarly, I need to do for val loader, and here it will be val set batch size equal to batch size, shuffle equal to true. And I just had to execute the very first cell so that all the imports worked properly, and then this undefined thing went away. So anyway, now when I went up to the last cell, I got these torch.nn has no attribute optim. That's because this one, it will be torch. Yes. All right. And now that all these training variables are defined, I can run the training by doing history equal to execute the train method. First one is epochs, then model. Let's quickly check out our arguments that it will take. Train method takes epochs, model, train loader, val loader, criterion, optimizer, scheduler, patch, right? So model, then train loader, val loader, criterion, optimizer, and scheduler. And when I started executing this model, I was getting this kind of result right after 3 epochs. That's only 3 epochs. Here by this time, the loss and the accuracy should not be any good. So at this point, I was getting a validation loss of 1.061 and validation accuracy of 0.704. Now obviously this 1.061 is a pretty bad loss because here we are using cross entropy loss, and that should be kind of less than 0.0304 to be called any good. But remember, this is a result I'm getting only after running 3 epochs. All right, now that we are training this model for quite a few epochs, we have to plot the loss and the score, IOU score, and the accuracy against the epochs. So let's define some methods in my utils file, and later I will execute that methods in my notebook to plot them. So the first method will be plot loss versus epoch. It will take that history object, which will have all my, remember, history object has all the train loss, validation loss, and train IOU, validation IOU, and also the accuracy saved in various keys. So plt.plot. And first I'm going to pick up val loss. And just I'm quickly checking that this is exactly what I saved in the history object. So let's come back to our, yes, so this is my history object. Let's copy it and just for referring. Some plotting function. And I'm just keeping this temporarily just for keeping a reference, because I need them during writing of my methods. So I need the val loss and label equal to val marker equal to, let's give it O. And then plt.plot. Now it will be my trend loss history. Oops. Okay, let's skip the trend, but val trend loss and label will be trend loss marker O. And then I need, actually this, I don't need this line. Why? The tab 9 auto intelligence was putting some crazy stuff sometime. Okay, now plt.ital for epoch and plt.ylabel loss. Yeah, actually just put this below. plt.x label will be epochs. Legend, and also plt.grid, plt.show. Now the next function will be epochs versus IOU. So plt IOU versus epochs, epochs. This string. plt.plot. I would need history. Again, the tab 9 intelligence is putting quite a few things. I don't need val loss here. I need train IOU. Actually, train MIOU. Label train MIOU, and marker included asterisk. And I need the same. I need the same for validation MIOU. Label val marker star. plt.ital score for MIOU score for epoch, and plt.ylabel would be my mean IOU, and plt.x label would be epochs. plt.show. Next one will be plot. Actually, let's plot. Next one will be plot the accuracy versus SCCURICY versus epoch history. So here I will take plt.plot history. I will take brain accuracy. Then label would be accuracy versus actually train accuracy, and marker will be GAN. plt.plot test accuracy. No, that's my validation accuracies. Label val accuracy marker star, and plt.title would be well actually just accuracy versus PTOCH. plt.ylabel will be accuracy only, and plt.x label epoch, plt.legend. I do not want to pass the LOC argument, and lastly plt.show. Cool. And now I have to come back here and execute those function and passing them these history objects. So let's do that. Plot loss versus epoch history. Then I need to do plot IOU and also accuracy versus epoch. And when I ran those three methods, this is the kind of output I was getting after running like 15 or so epochs. So my loss is decreasing like this. Then the MIUU, mean intersection over union, was increasing, and also accuracy per epoch, that was improving as well continuously. So overall it looks like a kind of good result, but now I have to do the evaluation part. But before running the evaluation, I should not forget to save the model, because I did not save it. Did I? In torch.save, I don't think I have saved it. So let's just write a quick one-liner. Torch.save model, and let's name it Inception-v4.pt, because I need to get this model, which is completely pre-trained by now, to be evaluated against my test dataset. So let's also go back to our data gen file, because now I am going to write the test data loader methods for loading my test dataset. So it will be almost kind of similar what we did for this data gen class, because that was loading my training data. So let's start writing. Data loading for test set class test data gen, and it will be inheriting from data set. Sorry. Okay, the first one is obviously the init method, self, it will take image path, then mask path, then x, then transform none, and self dot image path equal to image path, self dot mask path equal to mask path, self dot x, it would be just x equal to x, and self dot transform equal to transform. Actually, I do not want to put any s over here. All right, now that's my first method, and then the len method. So it will take self, return len of self dot x, then get item, and it will take index. So first I need to take just like the get item method of my training data gen class. That is, I need to do the cv2.imRead, then cv2.cvtColor, convert color, and then again imRead with the mask path, the file type, and also imRead grayscale. And then I need to do the self.transform is not none, and apply the augmentation. Yeah, so let's just go ahead and do that. It will be just similar. Okay, get item image equal to cv2.imRead self.image path plus self.x idx. Then I need to pass the file ending time .jpg. So I'm getting the image here from array. Similarly, I need to get the mask. Right, yep. From here, self.transform is none. Then In that case, just return the image as it is after, of course, doing the form array. Self image path. Yeah. All right. So now mask equal to torch dot from numpy. So overall structure of this code remains exactly the same what I did for the train data loader. Test. Again, I'm doing some augmentation from augmentation library, just like in the train set. So the first one is resize. Why it's saying test data loader is not defined? Let me see. Right, so I have defined this as test data gen. So yep, no, it's all right. There was an extra tab space here. So first argument is root image path. Actually, let's take these to the Jupyter notebook. Otherwise, I will get a variable not defined error continuously. So now I am in the section of evaluation of test dataset, and here I do this. The first line is just defining all the transformation or the augmentation that will be applied on the dataset, test dataset, and then my actual test set is root image path, root mask path, then x test and transform equal to tcast. And again, I need to define few methods here. And if you have forgot, we used this in here in our notebook where we are executing all data loader methods. That's where we used this mean and std, and these were applied in our while generating the train set and validation set for before our training, this mean and std. So I'm going to use the same one here. Now it's I'm in the evaluation stage on the test data set, so I'm going to do model.eval, applying all the transforms, compose. image. Similarly for mask. I do not need to have the gradients here, so I'm declaring this context manager. And I have to unsqueeze all the extra dimension from the tensor. So unsqueeze is QUEEZE 0. Now I'm going to predict the image, which will just be model, and to that I will pass image. So now I have the predicted image and the mask, so I can calculate my mean IOU SURE. Sorry, mean IOU. That was our method name, mean IOU, predicted image and mask. Take the argmax, predicted image along dimension equal to 1, and also I need to transfer it to the CPU and squeeze. And now I can return. So that's one method. I have to write a similar method for the pixel accuracy. Same mean and standard deviation. Otherwise, some of the operations will be the same. I have to apply the transform. I have to move the model and image and mask to the device. Then with torch.nograd context manager, I have to unsqueeze them, get the predicted image, and calculate the pixel accuracy. So let's just code it up. E dot compose. Pixel accuracy. Pixel accuracy will be the invocation of our earlier defined method, pixel accuracy. To that, I have to pass the two arguments, which are my predicted image and mask. And now I have to get the argmax. Predicted image deem equal to. All right, so these two are done. And once again, remember that this model here is fully trained now. So, and all these all these codes under the section evaluation of the test data set, I am using this pre-trained model to evaluate my test image set. All right, so I am almost towards the end of this project. Now I have to so now that I have my predicted mask, my image and the original mask, I can plot them side by side to that is, I can plot the original image, then the mask of the original image, which was given as in my training set, that is a ground truth mask, and also the predicted mask, and see the comparison. So I am going to do 3 plots side by side. That would be equal to plt dot 1 row 3 column. Is equal to, let's do 20 by 10. That's the original image. Set title. Now I have to do similarly for my mask, ground truth mask. So ax2.im show. Remember, this mask is my coming from here, image mask test set 3. And now finally the third column will be my predicted mask, ax3 im show. How did I get this? That's from here. Invocation of this function, predict image mask MIOU, that will give me the predicted mask and also the MIU score. Predicted mask. All right, and set X is off. Okay. Here also this one is original image, then the ground truth mask and the predicted mask, and we can see the predicted mask is almost similar to the ground truth. And the functions that I have to write now are for predicting the image mask MIOU, that is a mean IOU on the test data set, and also for predicting image mask pixel accuracy. So let's go to our utils file. The first one is for mask image and mask MIOU. Predict. For the mean, I will give the mean that we have used earlier, which is this. And similarly for the standard deviation, I'm going to use the same one that we have used earlier. And now I need to just invoke these two methods. So let's go to our notebook. I have the test set defined. Oops, this will be equal to. I have my test set defined. So now I can do, let's get the image and mask from my test set. Take the 3 indexed element, and I also need pred mask, and score will be the invocation of the method predict. What was the name? Oops, sorry. The name is predict image mask MIOU. To that I pass model, image, and mask. And now I also need another method called for getting the MIOU score from the trained model. So let's go to our utils file. Model and test set. Note again that this test set is just the output of the test data generator function. That is, it is going to supply the test data set to the model after generating it from data loader module. Here I said score. Let's define the list. Set. I need image and mask from each of the elements of test set I, and then I need the predicted mask and score by invoking the predict image mask MIU method. Predict then I just append these score, that is MIOU score, to the score IOU. Got it. And score, yeah. similarly, I need another method for getting the pixel accuracy from trained model. Structure will be just the same. That is, I'm going to get my predicted mask and accuracy from invoking this method that we just wrote, predict image mask pixel accuracy, and then append those accuracy to a list and return that list. Pixel accuracy from TRAI trained model test set accuracy equalizer PDM range len test set mask equal to test set I and I need this function. Cool. Now let's go back to my notebook here. In the next cell, I get the test set. I have already so after this line, I also need the test set MIOU, which will be equal to MIOU SC this function. And then why it's saying okay, it's saying not defined because I did not run this cell. Then similarly, I need the test set. I need the test set accuracy set, which will be pixel from trained model. To that I pass. Cool. And here is that result. So on the left I have the original image, then the middle, that is a column number 2's plot, is the actual mask, ground truth mask, and this, the far right one, that's a predicted mask. And visually we can see that the predicted mask is almost resembling the ground truth. That means the prediction has been quite good. And I did the same for another set here. That is the same code that I used here. Again, the same I did for another set, that is test set 4, and here also I got pretty much a good result. That is and the point to note here that we got such a good prediction that we can check visually, and that's because after we ran 15 epochs, the last loss score that I was getting on validation set was this. Where is that? At the end of at the end of 13 epoch, I got the validation loss of 508. That is 0.508. That's my cross entropy loss, and train loss was 0.579, and validation mean IOU that I was getting is 0.507, and train and validation accuracy that I was getting is also was pretty good, 0.844. So that's only after running 13 epochs. that pretty much wraps up this video, and all my upcoming videos will all be on some great computer vision projects and algorithm with PyTorch and TensorFlow. So stay tuned, and if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. Thank you for watching.